So I've had some questions about how the mouse can be used to drive our helicopter around. So I'm going to do a little tutorial here to try and help explain that to you. So basically, I think of what we have is a helicopter. This rotor going around, and the only thing acting on it at the beginning is the force of gravity. And if you did the bouncing ball experiment, this is what we basically use. We just use gravity to pull the object down and bring it down to ground. And what I'm asking you to do now is use you think of controlling the helicopter as like a joystick that can move in any of these directions, and you also have the Z and the X key, which will increase our rotor speed. Right, so that's what we need to mimic. So the first step, step one I would say, is get the Z and the X working so that all you have is the rotor speed increasing going against gravity. So we'll have I'm just going to call it Ft, force of our thrust. And it's going to be directly in the Z direction, because here's our coordinates that we're using with OSG, so Y is into the screen. And here's our X, and here's our Z, right? So initially you'll just have, hopefully, your helicopter going up and down along that Z axis. Okay, and that takes care of the increasing the rotor speed. But now, what about when we want to have this guy move? So let's imagine if you want to just move it forward slightly so that our helicopter should drive forward. Okay, so let's take a look at what that means. So if I draw another little diagram here, X, Y, Z, then my vector, which was going straight up, right, because that's where we basically had for increasing the Z key, our helicopter just go up and down. But now we want to make it go forward, so we're going to actually change our vector from straight up. It's going to be slightly this way, at some angle. And there'll be nothing in the X component. So there, if we look at the breakdown of the vector, Ft, if you want to call it that, would be equal to, and these are vectors, Ft in the Z direction plus Ft in the Y direction and Ft in the X direction. So in this example, there'd be nothing, right? There'd just be this angle we call theta there. So initially, Ft was, we'll say, equal to the force of gravity, negative, I guess, because let's say it was able to be equal, meaning depending on the initial velocity. Let's say it was initially equal to that, then it would be stationary. If there was an initial velocity, then you'd be still going at that velocity, whatever it was beforehand. But if it was initially at this, it would be hovering. So we bend the stick forward, we create this theta angle, and our equation now breaks down to this. So how do we get the mouse to mimic that behavior? Okay, so let's look at This is the mouse. And the mouse only has x and y coordinates, so we'll just draw a box over here. And there's our x, and there's our y. So if we move our mouse straight up, let's draw it in red, just like we suggested that we were going to do. So we're going to tilt this thing forward. So the mouse acts just the same way. We're going to move the mouse forward. So initially it was at that location. Let's say it's, well, let's just say for simplicity it's coordinate 0, 0. And now it's at coordinate 0, 50. So we have some vector going straight up. So what we need to do is we're going to take the magnitude of this vector. Let's write that down. The magnitude of this vector will translate into theta. So however much you move your mouse forward, then that's going to be simulating moving this joystick farther forward, which would cause a tilt in our vector and this theta. So it's not a direct mapping. You can make it be whatever you want. So let's say that this magnitude was equal to 50 in our case, and let's say that it was the most deflection you wanted. So that was almost like stomping on the gas and pinning our accelerator, going straight forward, making our helicopter go straight forward. That magnitude of say 50 could equal a theta of 15 degrees, which is our max theta we wanted. Okay, so we have a linear relationship then. So a magnitude of 25, which would mean our vector went halfway, then that would be equal to 7.5 degrees of a theta. Okay, so that gives us theta. So let's write our original equation now. If you remember from the physics lecture we took a few weeks ago, we said that F of t, so the overall thrust, was equal to, and I've already drawn this up before, Ft. And I think I'm not using the exact correct notation. It should be like x hat, y hat, z hat, meaning vectors. But let's just see if we can make this clear. Ty plus ft x. Okay, so ftz equals to ft cos theta. So whatever our theta was at the beginning, or sorry, our ft, our thrust, and we've now moved that vector to this location, we need to bring it back to the z component, so we need to take the cos of that theta, this angle here. And we now have the z component. Okay. Now remember how we do this is we have to project this vector. Let's say that this vector was not right along the y-axis. Let's say it was out slightly. Let's do this in green. Let's say it projects down, straight down onto this plane in this location. And we said that, extend that angle. This angle here, from the x-axis going towards the y, was an angle called phi. And we'll talk about how we can determine phi in a minute, okay? But we're just going to write down our original equation. So we know theta because that's the magnitude of our mouse movement. So ft y equals ft sine theta sine phi. So that's the fty component. The ftx component would equal ft sine theta cos phi. And this is essentially just using the old SOHCAHTOA. Oops, H there. TOA formulas, right? So there we go. There's our forces in the FTZ, FTY, FTX direction. And the only negating force is FG, which is directly against this guy. Okay, so let's talk about how we can solve for this phi. How do we get that? Okay, so going back to, we'll draw another diagram of our mouse here. So here's our mouse. Again. And let's say, so that's X and that's Y. Let's say, in this case, we're going to move our mouse in a diagonal direction. So not straight up and down, but in a diagonal direction. Okay, so let's say we move the mouse. So the mouse, if we draw the mouse, it was here, and then we moved it along our desk to this location. So the vector might look something like this, it went straight that way. Now, what did we already say? We already said the magnitude of this guy. So the magnitude, which is how long that vector is equal to theta. And we directly translate that. And this angle that we have here, this angle turns out to be phi. And I gave you a vector 2D class that takes a vector and will give you, well, actually the vector, we have to do a tan 2 on it. So let's take a look at that. Okay. So we're going to get the vector 2D class allows us to plug in the x, y coordinate. And we get that basically by saying the original mouse location was here, which was some coordinates. We can use the get x, get y. And now when we move the mouse, we can retrieve the new x and y. And so there's our, and the delta of those x and y's are going to be delta x and delta y. Will be the x and y of our vector 2D class that we plug in. And then we take the atan 2, which is a function call, and we pass in y, comma, x, and that spits out phi. And that's in radians. Alright, so there we go. So we've solved for both theta and phi. Theta is the magnitude of how fast you moved your mouse from one spot to the other, so the magnitude. And the angle at which you moved it is going to be the phi. And how we resolve that is we use that atan 2. And this is actually in the test code that I gave you called, what was it called? Vector normalization, I think it was what it was called. And the only wrinkle was, in their test code, is they swapped these parameters by accident. So I think that they had a little bug there. But you want to have it y comma x, and I believe they had x comma y, so you have to be aware of that. But now that you have theta and phi, you just use these formulas right there. And you can move your helicopter anywhere. Now the only problem, it's very hard to control your helicopter because if you accelerate a little bit more than, say, gravity, you start going up, and if you, let's say you set the force to be exactly gravity, the rotor speed, well, because you have an initial velocity, you just keep going up. So you got to decrease your rotor speed which means you're going to go down, and then you accelerate down, and then you want to go back up, so you start hitting the Z key to go back up, and it's very difficult to control that. So we're going to probably come up with some other scheme to help us with that. But nonetheless, that's the basic nuts and bolts for getting this working. I hope that helps you finish the milestone 1. Okay, thank you.